Welcome back to Harryverse. Tonight we explore the strange interstellar visitor 3I Atlas and why almost everyone has been wrong about it. If you enjoy these calm, mysterious space stories, please like, subscribe, and share this video so the channel can keep growing. Thank you so much for watching. And I'm curious, when and where are you listening right now, late at night in your room, on the bus, or somewhere else? Tell me in the comments. 3I Atlas moves outward now, away from the inner solar system and back toward the thin darkness between the stars. Its path takes it steadily farther from Earth, and with every passing day it grows dimmer in even the most powerful telescopes. For a short window in cosmic terms, though, almost every major observatory that can see it has turned to look. This is not just another comet from the outer reaches of the Sun's domain. It is an interstellar visitor, a body that formed around another star and drifted through the galaxy before intersecting this small planetary system by chance. The chance is brief and unrepeatable. There will never be another opportunity to observe this exact object again. That pressure shapes everything that follows. Astronomers know they are watching a one-time event. They do not get to adjust the orbit, slow the motion, or ask the object to return. It passes through on its own schedule, pulled only by gravity and pushed only by sunlight, and the only option is to gather as much information as possible while it is here. When 3I Atlas swings past the Sun and back out toward the outer system, Earth receives a moment of unusual closeness in the final days of the encounter. In the closing weeks of the year, when most of the world focuses inward, telescopes instead turn outward for one last detailed look as the object recedes. For a long stretch before that, the visitor hides behind the glare of the Sun, lost in the overwhelming brightness that saturates detectors and drowns faint objects. During that time, something important happens. The surface of 3I Atlas bakes in intense radiation and heat. The side facing the Sun warms, its frozen materials begin to sublimate and escape, and whatever structure lies beneath the outer crust starts to respond. Those weeks are invisible to direct observation, but critical in the story. When the object emerges again from the solar glare and becomes visible to instruments, it is not quite the same as before. It is brighter in some wavelengths and stranger in shape. What returns to view is the same interstellar body, but the Sun has changed what lies on and just below its surface. Ground-based observatories and space telescopes share this last act. The Hubble Space Telescope records a point of light wrapped in a hazy envelope known as a coma, a cloud of gas and dust that has been liberated from the surface of the solid nucleus. This is a familiar structure. Comets in the inner solar system have been observed this way for decades. The general pattern is simple. A small, icy core heats up, its ices turn to gas. The gas drags dust along as it escapes and sunlight, and the solar winds shape that material into a broad tail that streams away from the Sun. That basic picture is one of the first things students learn about comets. It seems solid, almost comforting in its simplicity. Yet 3I Atlas refuses to stay inside that picture. In raw images, the object looks like a bright dot surrounded by fog, but the fog hides critical detail. To see more, astronomers process the image with a technique that emphasizes structures that are not circular and smooth. In that processed view, the neat spherical coma falls away, and narrow jets of gas and dust appear like scratches in the glow. On one side, a broad feature stretches away from the nucleus. It behaves like a tail, but it points almost directly toward the Sun, not away from it. This is the first quiet violation of expectation. Comet tails are supposed to lean away from the Sun because charged particles streaming out from the solar surface sweep dust and gas backward. The solar wind is not wind in the usual sense. It is a flow of high-energy particles and radiation that fills interplanetary space strong enough to push on small grains of matter. Over and over across the history of comet science, this pattern has appeared. The coma forms around the nucleus, the tail trails the coma, and the whole structure points away from the Sun. It becomes a kind of mental template. 3I Atlas does not match the template. Instead, as observations accumulate, the tail that faces the Sun persists. Its technical name is an anti-tail, a configuration that can appear under special geometric conditions when particles are arranged in a thin sheet, and Earth looks at that sheet from just the right angle. Anti-tails have been seen before, but usually as a transient trick of perspective, a brief curiosity, before the normal pattern returns. In this case, The sunward feature endures through a significant portion of the object's passage, including times when the geometry should favor a more ordinary appearance. The closer the object gets to the sun, the more forcefully the solar wind should blow outward, and the more the familiar tail should dominate. Instead, a strong jet or sheet of material on the sunward side stays visible, apparently resisting or even overcoming the outward push. That persistence implies energy not just from sunlight, but from within the object itself, pushing material out in a way that competes with the star at the center of the system. On the opposite side of the nucleus, something even more intricate appears. The processed images reveal a small group of narrow jets, three main features fanning out with almost geometric precision. One aligns roughly where a standard tail should be. Two others branch to the sides so that taken together they sketch a triangular pattern in the surrounding haze. It is not a perfect triangle, but it is coherent enough to stand out in scientific images that normally tolerate a great deal of randomness. Jets from comets often emerge from regions where sunlight strikes fissures or exposed patches of volatile ice. They can be messy, irregular, and time variable. Seeing a trio of similarly bright, similarly narrow structures arranged in a stable pattern naturally suggests that something below the surface is producing them in a coordinated way. This is where the long history of speculation about interstellar visitors begins to intersect with the raw data. An object that arrives from interstellar space shines in an unusual way and displays apparently structured features will always invite more exotic interpretations. The human tendency to project intent and design onto unusual patterns is strong, especially when the subject is a lone visitor from another star. The idea that 3i Atlas might be a craft or a probe, or might contain some engineered element, arises almost immediately in popular imagination. Yet the scientific teams who work directly with the data move more slowly. They catalog what can be measured and what cannot. The brightness of the coma, the rate at which dust appears, the orientation of the tail features as the object moves. All of these can be quantified, and each new measurement offers both an anchor and a challenge. Some details fit within existing comet behavior, especially if one allows for extreme viewing geometries and rare surface structures. Other details resist that, at least at first glance. The result is a strange combination of familiarity and discomfort. A bright nucleus, a coma jets and tails all fit within the category of a comet. A sunward anti-tail that remains strong near the sun, and a triangular arrangement of jets are harder to fold into that category without stretching the definitions. The label of comet remains, but the object under that label grows harder to summarize. As analysts process more images and compare them across time, they see changes in the shape and brightness of the jets that hint at rotation surface fractures and evolving vents. Nothing stays fixed, yet certain oddities repeat enough to demand explanations in terms of physics rather than coincidence alone. 3i Atlas becomes a test of how far current models of ice, dust, heat, and gas can go when applied to a body that did not grow up under this sun. What began as a distant point of light now carries a complicated identity. It is an interstellar object showing comet-like behavior, yet with tails that lean the wrong way and jets that sketch unfamiliar patterns. That complexity is what draws deeper attention. Each observation that brings the object more firmly into the category of natural comet also reveals a detail that does not quite sit comfortably there. The more it is studied, the more it behaves like something that is both normal and misaligned, as if an ordinary process has been taken to a place where the usual assumptions no longer strictly apply. With every passing day as the visitor draws farther away, that tension between normal and abnormal becomes sharper, not softer. The data set is finite, the viewing window is closing, and the unanswered questions press more firmly against the edges of what is known. 3i Atlas continues on its path either way, indifferent to the interpretations that trail behind it across the sky. 3i Atlas now stands at the center of an intensive campaign to understand how something so familiar in outline can behave in ways that refuse simple explanation. The basic ingredients look ordinary enough. A small solid nucleus made of frozen gases and dust travels along an elongated path past the sun. As sunlight reaches its surface, the outer layers warm, and the most volatile ices begin to escape directly from solid to gas. That gas carries dust with it, and together they form the diffuse envelope, called the coma, that wraps around the nucleus as a pale shell. This structure sits inside the larger influence of the solar wind, the steady flow of energetic particles and radiation moving outward from the sun in all directions. Under that flow, small grains of dust feel a persistent push, and an extended tail normally streams away from the sun, pointing roughly in the opposite direction of the incoming light. Against that background, the pictures of 3I Atlas from Earth orbit and from ground-based observatories look at first glance like another confirmation of what is already known. There is a bright central point that marks the nucleus. Around it spreads a hazy sphere of illuminated material that grows larger as the object comes nearer to the sun. There is structure in that haze, faint hints of asymmetry and straight-edged features, but these vanish beneath the overwhelming brightness of the main coma. To extract the subtle elements, astronomers return to processing techniques. One of the most useful is the rotational gradient filter. In simple terms, it enhances what changes rapidly with direction, while suppressing what is smooth and circular. When applied to comet images, it strips away much of the uniform brightness of the coma and reveals the thin strands of jets and tails that rise above that background. The filtered view of 3I Atlas quickly becomes the more interesting one. In place of a roughly symmetric cloud, it shows a set of narrow features that mark material streaming away from specific regions on the surface. On one side of the nucleus, a broad band extends roughly toward the sun instead of away from it. This is the anti-tail, the most visually striking sign that something unusual is happening. Understanding that feature requires both geometry and physics. Anti-tails are not completely unheard of. In certain configurations, dust released from a comet can settle into a thin plane that includes both the comet and the sun. If Earth happens to move through that plane, the view down its thickness can make dust that is actually trailing along the comet's orbit appear to extend toward the sun. Perspective alone can create a sunward pointing streak. In many documented cases, careful modeling of the orbit and the viewing angle shows that this explanation is sufficient. The feature appears only for a short interval while the alignment is exact and fades as soon as the geometry shifts. At first, many researchers expect that 3I Atlas will follow the same pattern. The strong anti-tail could arise from an especially thin debris sheet, combined with an unusually precise viewing angle. If that is the case, the tail should rotate and weaken as the comet and Earth move along their paths. Yet, as more images accumulate, the expected fading does not occur in a simple way. The sunward feature persists across a wider range of angles than is comfortable for a purely geometric explanation. During the period when 3I Atlas is closest to the sun, when the solar wind pressure on dust grains should be greatest, the anti-tail remains prominent. This pushes some groups to look beyond projection effects and consider the possibility that real physical jets on the sunward side are contributing. In this view, sunlight heats vents or fractures in such a way that material erupts preferentially toward the sun, and the resulting outflow is strong enough that it is not immediately swept backward. The jet might then arc away under the influence of the wind, but a dense near region could still line up along the sunward direction. To test such ideas, teams compare images from different times and wavelengths, and match them with models that include both dust dynamics and gas flow. As this work proceeds, a more layered picture appears. The coma of 3I Atlas contains multiple grain sizes and gas species. Larger grains respond slowly to the solar wind and may linger near their point of release, while smaller grains are carried off more quickly. Gas molecules behave differently again, driven both by thermal expansion from the surface and by interactions with sunlight. If the surface of the nucleus is uneven, with some regions buried under insulating material and others freshly exposed by fractures, then different areas activate at different times. Some begin venting only after penetrating heat reaches them, creating delayed outbursts. In this context, the anti-tail may record not just a static geometry, but a sequence of activation events. The sunward side of 3I Atlas experiences the highest flux of energy as it rounds the sun. If buried pockets of volatile material lie not far beneath a relatively thin crust in that region, the heating can build until it finally exceeds the crust's ability to confine it. When that threshold is reached, gas escapes in a focused eruption that preferentially sprays dust toward the sun before the solar wind has time to rearrange it. Observations taken at different dates hint at changes in brightness consistent with such episodic behavior. Periods of enhanced activity correlate with subtle shifts in the shape of the antitail, suggesting that at least part of it is not a passive geometric illusion, but an active plume shaped by an internal energy reservoir. The comet-like label still fits, but the distribution of energy between sunlight and interior pressure looks different from the simplest case. On the opposite side of the nucleus, the processed images show something that is harder still to fold into standard scenarios. Instead of a single broad tail, 3i Atlas often displays a cluster of jets that, when traced outward, create a roughly triangular pattern in the surrounding halo. One jet occupies the approximate direction of a traditional tail pointing away from the sun and shaped by the solar wind. Two others branch off at smaller angles, forming a three-sided figure that stays recognizable across multiple observations. This implies that the active regions on the surface are not distributed randomly. They may lie along a band or some repeating structural feature, such as the edge of a large fracture. As the nucleus rotates, those vents sweep through space, but the combined pattern averages into a shape that retains its triangular signature. The triangle does not mean design, but it does indicate underlying order. This is the kind of detail that brings speculation about artificial origins into public discussion. Yet inside the observatories, the focus stays on the physics of irregular bodies. Comet nuclei visited by spacecraft have shown cliffs, pits, layered walls, and strange lobes, all shaped by slow erosion and occasional breakup. If 3i Atlas began as a more typical comet in another system, then it likely shares the same tendency to develop complex topography. In that context, three bright jets arranged in a triangle could mark facets of a fractured block or mouths of a buried cavity that broke open along preferred directions. The fact that such arrangements are rare in the local population only strengthens the sense that this object has followed a different path. Every new image helps to refine this view. As 3i Atlas recedes, the coma grows fainter, but improvements in processing continue to draw out thin structures in the tail. Comparative studies with other comets reveal both similarities and sharp differences. The brightness profile of the coma, the rate at which dust density falls with distance from the nucleus, and the way the tail curves under the influence of solar wind all provide clues. The conclusion forming in many working groups is that 3i Atlas is not violating the known laws of motion or thermodynamics. Instead, it occupies an extreme corner of parameter space. Its combination of composition, internal layering, rotation, and exposure history to intense radiation has sculpted a surface that responds to the sun in a way that looks peculiar from the vantage point of Earth. The coma and the crooked tail are therefore not a sign that nature has changed its rules, but that this particular object has spent a very long time under conditions slightly different from those that shaped local comets. In the quiet rooms where teams compare models to data, this realization brings both relief and a new kind of mystery. The relief comes from seeing that basic physics holds. The mystery lies in the question of what kind of environment could produce a nucleus that carries such a different configuration of volatile pockets and fracture lines. The coma and its strange tail become not just features of the present encounter, but signatures of an earlier era in a different planetary system written in dust and gas, and only now becoming legible as the object moves through the inner regions of this one. In the processed images, 3i Atlas becomes less like a simple cloud and more like a machine drawing its own diagram in space, not through intention, but through the way physics shapes escaping material. The rotational gradient filter and related methods reveal knots and filaments that were invisible in raw frames, outlining paths where gas and dust have been focused into jets. In some exposures, the nucleus itself is not resolved as a disk. It remains a point smaller than the telescope's ability to separate into a surface. Yet the behavior of the surrounding material allows astronomers to infer what the hidden body is doing. Narrow jets fan outward in specific directions, and their brightness and curvature change over time. By following those changes across sequences of images taken over many nights, teams estimate a rotation period. The nucleus seems to spin not in a perfectly stable way, but with slight irregularities that may indicate a complex shape or a tumbling motion. When a jet brightens as a particular face turns toward the sun and dims, when it rotates away, it marks the location of an active vent on that face. In this way, a map of invisible terrain slowly emerges from the behavior of the coma. For 3i Atlas, the map looks crowded. Multiple vents appear to be active at once, and some of them show behavior that does not match simple models of smooth melting. Instead of a steady flow, there are hints of pulsing. Periods of quiet emission are interrupted by short-lived surges, suggesting that gas builds up behind partially blocked passages and then escapes in bursts. When these bursts occur on the sunward side, they feed the persistent anti-tail. When they occur on the night side or near the terminator between day and night on the nucleus, they contribute to the triad of jets that sweep backward. In longer exposures, faint arcs curve away from the main features, likely tracing older jets that have been bent by the solar wind and the comet's motion. This layered structure gives the impression that the object has been breathing in a complicated rhythm during its approach and departure, each exhalation leaving a trace that slowly drifts downstream. The jets themselves are not composed of pure gas. Embedded within them are grains of varying size, from microscopic dust to small pebbles. The gas provides the pressure, but the dust provides the visibility. In some observations, a change in brightness in a jet may reflect a change in the number of grains lifted, rather than a change in gas production alone. Spectroscopic studies which separate the light from the coma into its component colors show emission lines from specific molecules. These lines indicate that carbon-based species and simple gases are abundant. Early in the encounter, carbon dioxide dominates with only modest signatures from water. This is the first chemical sign that 3I Atlas is different from familiar comets near this sun, which usually produce copious water vapor as they warm. The dominance of carbon dioxide is important because it sublimates at lower temperatures than water ice. This means that even when the object is still relatively far from the sun, carbon dioxide can escape in significant quantities, powering jets from a surface that is still too cold for deep water reservoirs to respond strongly. This explains why the coma of 3I Atlas appears active at distances where many local comets remain quiet. It also sets up a layered structure in the near subsurface with a carbon dioxide-rich outer shell overlying more stable ices. Jets powered by carbon dioxide can drill and widen fractures, exposing fresh material and gradually undermining the integrity of the crust. When the object draws closer to the sun and surface temperatures climb further, these pathways become ready-made channels for more volatile reservoirs deeper inside. Telescopes operating at different wavelengths each contribute a piece to this picture. Optical images capture the reflected sunlight from dust grains. Infrared observations probe heat and can reveal the temperatures of different regions in the coma. Radio telescopes sensitive to specific molecular transitions listen for the faint signals from gas as it rotates and vibrates. Taken together, these data show that the jets are not uniform streams. Some are richer in dust, some in gas, and their compositions shift over time. On certain dates, observers report that the sunward jet is comparatively dust-heavy, while one of the side jets appears more gas-dominated. This uneven distribution hints that the vents feeding them tap into different layers of the interior. Perhaps one reaches a pocket where small grains are loosely bound and easily lifted, while another vents a clearer gas reservoir. This variation supports the idea that the nucleus is not a homogeneous block, but a stratified structure shaped by a long and complex history. The triangular arrangement of jets on the nightward side becomes more interesting in this context. If each jet has a distinct composition and time profile, then the apparent geometric regularity may arise not from symmetry in the crust, but from the way deep fractures intersect. One scenario imagines a buried cavity whose roof has been weakened by cosmic radiation and micro-impacts over vast spans of time. Cracks radiate from this region, and when internal pressure rises, gas finds paths along these pre-existing weaknesses. Where three major cracks intersect the surface, three vents open roughly spaced. As the nucleus rotates, these fixed locations spray material into space in repeating arcs. The cumulative effect integrated over many rotations during a single long exposure is a triangular fan of jets. Most of this remains in the realm of model and inference, but it is constrained by concrete measurements. The angles between jets, their relative brightness, and the way they vary with the object's position around the sun must all match the geometry of any proposed interior structure. As teams adjust these models, they also examine the way the jets influence the motion of the comet itself. When gas escapes from a vent, it imparts a small thrust in the opposite direction, like a constant series of miniature rocket firings. For most comets, This non-gravitational effect is small but measurable. Over many weeks, it slightly alters the orbit compared with the path predicted by gravity alone. In the case of an interstellar object like 3I Atlas, which spends only a short time under the Sun's influence, these effects are subtle, yet they can still be detected if the jets are strong and asymmetric. Some analyses suggest that the unusual pattern of jets may give 3I Atlas a gentle push that modifies its exit trajectory by a tiny amount. This does not keep it bound to the Sun, but it does mean that the path it takes out of the solar system is not precisely the mirror of the path it took in. In a sense, the object leaves with a different trajectory than it arrived with, shaped not just by the Sun's gravity, but by its own eruptive behavior. To those who consider more speculative possibilities, such fine steering invites questions. Could an artificial object use controlled jets to adjust its path in a similar way? Would such non-gravitational accelerations look different from those caused by natural outgassing? The case of 3I Atlas provides a partial answer. The observed jets and their effects can be explained by natural sublimation processes driven by solar heating, especially given the unusual composition and layered structure inferred from spectra. There is no need to invoke engineered control to account for the measured deviations. At the same time, the case illustrates how difficult it can be to distinguish subtle artificial thrust from complex natural outgassing, especially when only remote sensing is available. In that sense, 3I Atlas becomes a practical benchmark for how far a natural object can go in mimicking some of the dynamics that might be expected from a controlled vehicle. The study of jets in the dark therefore serves a dual purpose. It advances understanding of cometary physics in extreme conditions, and also refines the tools that would be needed to recognize truly unnatural behavior in future interstellar visitors. As the interstellar comet fades, the processed images and their detailed structures remain in archives ready to be reanalyzed when new theories emerge or when another object with similarly puzzling jets appears in the sky. They are the fixed record of a set of events that played out once and will never be repeated, a frozen choreography of gas and dust that encodes the internal story of a small body that has crossed both the galaxy and human imagination. 3. I Atlas does not only look strange, it also exhales a chemistry that sits at odds with what decades of comet studies have taught astronomers to expect. Long before the object reached its closest point to the Sun, observatories began splitting its light into spectra, turning a faint blur into a pattern of lines that reveal what molecules are present in the gas flowing away from the nucleus. For comets that belong to this system, the pattern has a familiar shape. Water dominates. When a typical comet from the outer reaches of the Sun's domain falls inward, its icy surface warms, and water ice sublimates, releasing water vapor that carries dust into space. Other gases emerge as well, including carbon monoxide and carbon dioxide, but they ride alongside the water as minor components. The entire framework of comet science has been built on that expectation. In that context, the first detailed spectral readings of 3I Atlas are quietly disruptive. Instruments that are tuned to the characteristic fingerprints of water vapor see only modest signals, while lines associated with carbon dioxide stand out strongly. Ratios that normally lean heavily toward water now tilt in the opposite direction. The interstellar visitor appears to be breathing in the wrong order, exhaling a gas that is usually secondary while keeping the primary reservoir unusually subdued. At greater distances from the Sun, this in itself might not be entirely shocking. Carbon dioxide can escape at lower temperatures than water, so there is a natural regime where carbon dioxide-dominated outgassing is expected. What makes 3I Atlas unsettling is how long this inversion persists, and how weak the early water signature remains, even as the object moves into regions where water in ordinary comets begins to pour out. Observatories repeat their measurements, calibrate instruments, and compare results between independent sites. The pattern holds. The coma is rich in carbon dioxide with traces of other simple molecules, but the water content seems unusually low. That observation adds a new dimension to the earlier puzzles of the anti-tail and the triangular jets. An object that vents mostly carbon dioxide is likely constructed differently from the water-heavy bodies that populate the outer belts of this system. It may have formed closer to its original star where different temperatures ruled, or in a region with a distinct chemical makeup. Alternatively, it may have started with a more familiar composition, and then had its outer layers altered by long exposure to some unusual environment. Either way, the chemical imbalance suggests a history that diverges from the standard narrative written by local comets. To understand the contrast, astronomers look back at the catalog of known comets around the Sun. Many originate in the distant Oort cloud, a roughly spherical swarm of icy bodies that extends far beyond the orbit of the outer planets. Others come from the Kuiper belt, a broad ring beyond Neptune, where icy planetesimals still orbit in a relatively flat disk. Across this population, repeated measurements have shown that water is the baseline constituent with other volatiles riding along. There are exceptions and variations, but the basic pattern is robust enough to stand as a kind of chemical fingerprint of this system's cold outskirts. 3I Atlas, by contrast, presents a different fingerprint. That difference is precisely what makes it compelling. If interstellar visitors all looked exactly like Oort cloud comets, they would be intriguing, but not distinctly informative. The fact that this one is chemically inverted suggests that it can serve as a direct sample of conditions around another star, with its composition encoded in the gases it releases. In the first phase of its journey through the inner solar system, 3I Atlas behaves like a carbon dioxide-driven comet. Its early coma seems to be a shell, composed of material that was either originally rich in carbon dioxide or has been transformed into it, possibly by slow processes acting over immense timescales. The gas emerges from near the surface, fed by layers that respond quickly to modest heating. Deeper inside, water ice likely remains cold and locked away, shielded by overlying material. As the object approaches the Sun and the intensity of incoming energy rises, that deeper ice stays dormant at first, even while the outer carbon dioxide-rich strata steadily erode. From a chemical standpoint, the comet is exhaling its outer history while keeping its inner archive sealed. Spectral studies from mid-infrared and radio observatories help to refine this sketch. Facilities like the Mercat Array in South Africa and other radio-sensitive instruments are able to peer through the thick dust of the coma to pick up faint signatures from water and other molecules that are less apparent in optical and ultraviolet data. Early on, these instruments confirm the weak presence of water, reinforcing the sense that the outermost layers of 3I Atlas are depleted in it. This absence itself raises questions. One possibility is that the original water ice near the surface has already been removed over many previous passes near a star, leaving behind a drier crust enriched in less volatile species. However, orbital reconstruction suggests that this object has not passed close to any star for extremely long spans of time before this encounter with the Sun. Its current path indicates a long stay in the cold and sparse interstellar medium with no prior visits to similar heat. That makes a history of repeated stellar passages less likely. Another possibility is that the outer layer began water poor, forged in a region of a protoplanetary disk, where water could not condense efficiently. That would imply a formation zone closer to the original star where higher temperatures prevailed. In that case, 3I Atlas would be a fragment from a different part of its birth system than the typical distant comets seen here, a piece of inner architecture, ejected with enough energy to escape entirely. The idea that this small visitor carries the chemistry of another star's warmer regions wrapped around a colder core is both scientifically plausible and narratively striking. It turns each molecule in the coma into a messenger from elsewhere, a sample of foreign planetary building blocks delivered by gravity rather than by design. As the object descends toward its closest approach to the Sun, the story changes. The increased heat penetrates deeper into the nucleus, eventually reaching layers where water ice remains abundant. At a certain threshold, that deeper ice begins to sublimate. The effect is not immediate at the surface. There is still an overlying crust that must crack and vent to allow the newly generated gas to escape. But as pressure builds in subsurface cavities, existing fractures widen and new vents open. When that happens, the character of the coma alters. Radio instruments that once struggled to detect water lines now register them strongly. Water vapor pours into the coma at a rate that rivals or exceeds the earlier carbon dioxide flow. The visitor begins belatedly to breathe like a comet from this solar system after all. This transition is not smooth. Over a span of days to weeks, observers report rapid changes in brightness and structure. Outbursts occur when pent-up gas breaks through weakened crust, carrying dust and ice fragments outward in temporary plumes. These eruptions feed some of the anomalous jets seen in filtered images, and may be responsible for shifts in the apparent intensity of the anti-tail. The chemistry of the coma tracks this upheaval. Waterline's strengthened carbon dioxide remains present, and the mix of other species changes in ways that hint at gradients inside the nucleus. The outer carbon dioxide shell and the inner water-rich heart are now interacting, their products mixing in the space around the nucleus. In this phase, 3I Atlas no longer fits neatly into a single category. It is neither purely carbon dioxide dominated, nor purely water-driven. It is an evolving composite revealing more of its internal diversity as heat unlocks successive layers. In laboratories and theoretical studies, researchers have long considered how long-term exposure to cosmic radiation might process the surfaces of icy bodies in deep space. High-energy particles can break apart molecules and rearrange them into new compounds, often converting simple ices into more complex organics and oxidized species. Over millions and billions of years, such processing can build up a crust with a composition very different from the pristine material beneath. The early carbon dioxide-rich behavior of 3I Atlas fits well with this picture. Cosmic rays could have gradually transformed an initially water-rich surface into an unusual mix of molecules with carbon dioxide as a prominent end product. Beneath that processed layer, protected from the full intensity of radiation, original water ice would remain. When the sun's heat finally arrives, it first liberates the processed shell, then with more effort begins to tap into the deeper reservoir. The pattern of measured gases over time maps onto this scenario with striking fidelity. From that perspective, the way 3I Atlas breathes wrong at first, and then begins to breathe more like a local comet later, is not a contradiction, but a timeline written in chemistry. The outer exhalations tell the story of long isolation in interstellar space, under the constant rain of cosmic rays, while the later bursts of water reveal the original substance that predates that journey. The object becomes a layered record of two environments, the birth system where it formed and the galaxy-wide radiation field it has traversed since. What remains uncertain is exactly how much of each layer exists, how thick the processed crust is, and how deeply the sun's heat has reached during this single brief passage. These unknowns keep the narrative open. 3. I Atlas. Even as it departs, continues to pose questions about how common such heavily processed interstellar comets might be, and whether their strange early chemistry should be considered a warning that first impressions of such visitors can be misleading. The initial image of a carbon dioxide-dominated ghost gives way to a more complex figure, one that carries familiar water in its depths, but only reveals it after being pushed hard by a new star's light. As 3I Atlas swings through its closest approach to the sun and begins to climb back outward, the balance inside it shifts. For much of its inward journey, the object has behaved as though wrapped in a skin of transformed material, exhaling carbon dioxide and other products of long-term processing, while keeping deeper water in reserve. That pattern begins to break when the heating reaches a critical depth. Solar energy no longer merely warms the outermost layers. It penetrates through the radiation-altered shell and into volumes of ice that have remained effectively unchanged since the object formed. From this point onward, the coma is no longer only a record of the surface, it becomes a window into the interior. The change is first noticed in the quiet traces recorded by radio observatories. Dishes arranged across dry landscapes turn toward a region of sky that to the unaided eye looks empty. They listen not for sound, but for faint electromagnetic signatures emitted when water molecules spin and vibrate in specific ways. Early in the campaign, these receivers pick up only weak hints of water in the gas streaming from 3I Atlas. As the comet approaches and the sun's light grows stronger, those hints grow into clear lines. Observers see the water signal rise sharply over a short interval. The implied production rate jumps, indicating that large new areas of ice are now being tapped. In some reports, the water output increases by factors that cannot be explained by minor changes in surface temperature alone. Something structural has given way. The best explanation is that the crust has been breached in multiple places, allowing pressurized pockets of water vapor to find paths to space. This breach changes more than just the gas mix. When water flows out with sufficient force, it lifts dust and larger ice fragments with it, altering the appearance of the coma. Regions that were once faint brighten. Jets grow broader and more irregular as recently opened vents feed them. Short-lived outbursts punctuate the steady flow, each outburst corresponding to a moment when a new fracture opens or an existing one widens. Telescopes that capture sequences of images over hours and days reveal these events as sudden changes in the shape and brightness of the inner coma. The bland glow of the earlier carbon dioxide-dominated envelope gives way to a more structured and dynamic scene. To many researchers, this is the phase where 3I Atlas most clearly reveals what it truly is. The earlier stage showed how the outside has been altered by cosmic exposure. This stage shows the original body inside beginning to assert itself. In comparative terms, the behavior of the newly active water-rich interior looks much more like that of comets from the outer regions of the Sun's own system. The rates of water production, the way the coma responds to increased heating, and the patterns of dust uplift all fall within the broad ranges already documented for local icy bodies. This supports the idea that at heart, 3I Atlas is not an entirely exotic object. It may be a relatively ordinary water-ice comet that has been wrapped in an unusual shell by conditions encountered during a long interstellar journey. The shell is what gave it its early chemical strangeness, and its partial disruption now explains the dramatic shift in behavior. From this perspective, the interstellar comet becomes a layered archive. The inner core records the conditions of a primordial disk of gas and dust around another star frozen in place as water and simple solids. Around that sits a rind of material reshaped by cosmic radiation and micrometeoroid impacts during billions of years in deep space, where no star has warmed its surface. When the object is finally captured briefly by the sun's gravity and drawn inward, these layers respond in sequence. First, the outer rind sublimates and crumbles, filling the coma with carbon dioxide and other processed gases. Later, as heating grows more intense, fractures penetrate deeper, and the core begins to participate, releasing water and dust that have been sealed away since before the object left its native system. The sudden flood of water detected by radio and infrared instruments is the moment when the archive opens. It is a moment that almost did not happen. Had 3I Atlas passed a little farther from the sun, the heating might never have penetrated deeply enough to awaken the core. In that case, Earth would have seen only a radiation-hardened shell, misinterpreting the true nature of the object behind it. The chance that the orbit brings the comet close enough to strip away part of that shell without destroying the entire nucleus is a narrow one, and yet for this single encounter it is realized. This lends a sense of contingency to the observations. What astronomers record in this passage is not only a property of the object, but a consequence of the exact path it follows past this particular star. Models that attempt to reconstruct the internal structure lean heavily on the timing of the water surge. By working backward from when the water production rises and how quickly it grows, researchers can estimate how thick the processed crust must be and how efficiently heat moves through it. If the crust were extremely thick and highly insulating, the delay between carbon dioxide-dominated activity and water-dominated activity would be longer, and the transition more gradual. If it were thin and fragile, the water surge would occur early and blend with the carbon dioxide outgassing from the beginning. The observed pattern sits in between these extremes. It suggests a crust of significant thickness built up over long exposure, but not so strong that it can withstand sustained heating near a star like the Sun. Heat diffuses through it over weeks and months, eventually reaching a layer where water ice is abundant. Once temperatures there climb past the threshold for sublimation, the internal pressure rises until the crust fails along its weakest points. This picture meshes well with what is known about cosmic rays in the galaxy. High-energy particles from distant supernova and other energetic events stream through interstellar space in all directions. When they strike the surface of an icy body, they can break apart water and other simple molecules, rearranging the atoms into a variety of products, including carbon dioxide and more complex organics. Over immense spans of time, this process gradually converts a surface layer into a chemically distinct zone. The depth to which this processing penetrates depends on the energy of the particles and the density of the material, but in many models it extends to depths of several meters or more. In the case of an object like 3I Atlas, which may have spent hundreds of millions or even billions of years in the diffuse regions between stars, this processed layer could be substantial. The core beneath, however, would remain largely shielded. The water surge detected near perihelion then acts as a probe of where that boundary lies. It notes the moment when the sun's influence overtakes the influence of the galaxy-wide radiation background, when heating from a single star reaches down to depths previously dominated by much slower processes. For planetary scientists and astrophysicists, this transition offers a rare test of theories that usually remain abstract. Calculations of cosmic ray penetration depths, heating timescales, and sublimation thresholds all find direct application here. If the models are correct, they should predict something like the observed sequence: first carbon dioxide, then mixed gases, then strong water as the object nears the star, followed by a fading pattern as it recedes, and cooling shuts down the deeper vents. The observed evolution of 3I Atlas broadly matches this, giving confidence in some key assumptions and drawing attention to the places where it does not. Those mismatches are where new physics or overlooked details may lurk. Perhaps the crust is more porous than expected, allowing heat to travel along channels more quickly. Perhaps the core contains layers of different grain sizes and compositions, leading to uneven outgassing. These details matter because they shape how the object reacts to starlight and how its orbit might be altered as jets push on it. As the comet departs and water production declines, the window into the core begins to close. The vents cool, gas flow slows, and dust settles into a more diffuse halo. The moment of maximum revelation is brief. Data from that interval, however, will be re-examined for years. Each spectrum and image taken during the water flood carries clues about the structure and history of the interstellar nucleus. Together, they support the idea that 3I Atlas is not a mysterious engine or a constructed probe, but a natural body whose very long journey has left it encased in a shell that hides its more ordinary heart. This conclusion, though, does not reduce the sense of wonder. If anything, it amplifies it. A small comet-like object born around another star spends an enormous span of time in the dark between systems, accumulating a crust written by cosmic radiation, and then, on a single passage near an unfamiliar sun, briefly exposes part of its original interior. The fact that Earth happens to be watching at that precise moment is both a scientific opportunity and a reminder of how much of the galaxy's history plays out unnoticed. 3I Atlas has carried its inner ice for ages, and now in the narrow window where it is visible, it shows enough of that inner self to hint at how many other such archives may be moving unseen through the spaces between stars. Long before 3I Atlas ever comes into view of any telescope on Earth, its story is written in its orbit. The path it follows through the solar system is not a closed loop, but an open curve, a hyperbolic trajectory that cannot be bent by the sun's gravity into a bound state. From the first precise measurements of its motion, astronomers know that this object is not a returning member of the sun's family. It arrives from far outside, sweeps through once, and then leaves again, destined never to come back. This alone marks it as an interstellar visitor, but the exact shape and speed of its orbit carry deeper information. By fitting the observed positions over many days and correcting for the subtle, non-gravitational pushes from its jet streams, can reconstruct the incoming direction with reasonable accuracy. 3I Atlas seems to enter the solar system from a region of the sky near the projected direction of the Milky Way's dense inner zones broadly toward the galactic core. This does not mean it was born there. The motions of stars, gas, and small bodies over vast times blur simple lines of origin. Yet the trajectory hints that the object has spent a long time moving in the inner regions of the galaxy rather than in the sparse outskirts. The speed at which it approaches, measured relative to the sun, is higher than would be expected for a body loosely bound to the distant Oort cloud. It carries a surplus of velocity, a hyperbolic excess that indicates prior interactions with the gravity of other stars or massive planets. To trace this backward is to step into a domain of probabilities rather than certainties. The galaxy is not a still backdrop. Stars orbit the center in broad rosettes. Spiral arms, wind and shear, and clouds of gas drift and collapse. Within each stellar system, planets form and migrate, sometimes ejecting smaller bodies through gravitational slingshot encounters. In this shifting environment, a fragment like 3I Atlas could have been born around one star flung into interstellar space and then spent immense spans of time drifting under the combined pull of the galactic potential and the occasional weak tug from passing systems. Dynamical models that simulate billions of years of motion in a realistic galactic environment suggest that such ejections are common. When a young giant planet forms in a disk of gas and solids, it can scatter neighboring planetesimals onto highly elongated or escape trajectories. Many are thrown far outward, but remain gravitationally bound, forming extended comet reservoirs. A fraction gain enough energy to leave entirely. Once free, they follow paths that are no longer tied to a single star, but instead curve gently through the galaxy's gravitational field as a whole. 3I Atlas appears to be one such body. Its long-term past cannot be reconstructed star by star, but its present speed and direction tell astronomers that it has been traveling independently for at least many millions of years. There is no plausible configuration in which it left a parent system only recently, and still arrived with its current energy and orientation. Any nearby stars that could have contributed to a recent ejection are either moving too slowly relative to its path, or lie in the wrong part of the sky. Working through these constraints, researchers conclude that for at least 10 million years, and likely much longer, the object has not come within roughly 1 light year of any star. It has moved through regions where the nearest stellar neighbors were always distant suns whose light and heat were too weak to disturb its surface or orbit in any significant way. In that sense, 3I Atlas has been traveling through a kind of gravitationally defined wilderness, a volume of space, where individual stars are little more than bright points. In that wilderness, however, space is not truly empty. A diffuse background of gas dust and high-energy particles permeates the interstellar medium. Among these components, galactic cosmic rays stand out as a persistent influence. These are particles, mostly protons, and heavier nuclei accelerated to high energies by explosive events such as supernovae and by other energetic processes in and around the galaxy. They move in tangled paths, shaped by magnetic fields, eventually filling the volume of the Milky Way in a roughly steady way. Any small body drifting through this environment is constantly bombarded by these particles. For 3I Atlas, this bombardment has continued for spans of time that exceed the age of complex life on Earth. Each cosmic ray that strikes the surface has the potential to break apart molecules, rearrange atoms, and create new chemical bonds. Over time, these individual events accumulate into a slow planetary scale transformation. Water and other ices near the surface are partially converted into different compounds, including carbon dioxide and organic residues. This is the process that theoretical models have long predicted would create a processed layer atop interstellar ice bodies. Observations of 3I Atlas's early carbon dioxide-rich coma give the first direct evidence that such a layer can be substantial and active. The interstellar journey also exposes the object to the occasional shock of passing supernova blast waves and the more subtle influence of galactic tides. When a massive star ends its life in a supernova, it sends a shell of heated gas and accelerated particles expanding through space. If 3I Atlas happens to be in the path of such a wave, the local density of cosmic rays could spike, intensifying the surface processing for a while. Galactic tides, on the other hand, are the gentle, large-scale forces exerted by the overall mass distribution of the galaxy. They nudge the paths of small bodies over tens and hundreds of millions of years, changing their inclinations and guiding them slowly toward or away from the dense central regions. The combined effect of these influences is to give 3I Atlas a history that is both violent and deeply slow. On short timescales, nothing much happens. It drifts dark and cold through a near vacuum. On long timescales, its path curves through different galactic neighborhoods, and its surface chemistry evolves under continuous exposure to high-energy particles. In that sense, by the time it reaches the solar system, the object is both ancient and newly shaped. Its core remembers the early conditions of a foreign planetary nursery, while its crust bears the imprint of the galaxy's larger life cycle, written in altered molecules. The direction from which it enters, broadly pointing back toward the inner Milky Way, underscores this. The galactic core is a region of higher stellar density, more frequent supernovae, and stronger overall gravitational potential. If 3I Atlas has been orbiting within those inner regions, it may have experienced a different balance of cosmic ray flux and tidal forces than small bodies in the more quiescent outer disk. In particular, a higher rate of supernova events could have bathed it in a more intense radiation field, for certain intervals accelerating the construction of its processed crust. When scientists look at its unusual chemistry and structure, they see not only the fingerprint of its birth system, but also the imprint of the galactic neighborhood it has crossed. The absence of close stellar encounters over at least 10 million years is itself a constraint. It suggests that the object has moved through corridors of space where the density of stars is not exceptionally high. Even in the inner galaxy, there are zones where stellar separations remain large enough that direct near misses are rare. The object's path may have threaded one of these zones, avoiding capture or disruption, while still passing through regions of elevated cosmic ray activity. Each of these details matters because it feeds into a broader question. How representative is 3I Atlas? If it is a rare survivor of a specific and unusual path, then its properties might tell an idiosyncratic story. If instead it is typical of a vast population of interstellar comets that share similar histories, then it may be the first direct sample of a common class of objects that quietly fill the spaces between stars. Statistical models of planet formation and dynamical evolution suggest that every star with giant planets should eject many such bodies over its lifetime. The galaxy should be threaded with uncountable numbers of small, icy wanderers. Only a tiny fraction will ever pass close enough to the Sun to be detected by surveys on Earth, and only a smaller fraction will be caught early enough for detailed study. 3I Atlas is one of those few. The ability to trace its motion and composition back through time, even in a rough way, therefore offers a glimpse into a much larger and mostly invisible population. The long journey through silent space becomes part of the explanation for why it looks the way it does now. The anti-tail, the triangular jets, the layered chemistry, all of these present features are tied to that extended past. Without billions of years of exposure to cosmic rays and millions of years of solitary drift, the surface would not have developed its strange outer shell, and the dramatic transition to water-rich outgassing near the Sun would never have occurred. What is most striking, perhaps, is how little of that history would be apparent without the brief, intense encounter with a luminous star. For eons 3I Atlas has carried its inner structure and processed crust through darkness invisible and mute. Only when it falls through the narrow, luminous zone around the Sun does that structure begin to express itself in the language of comae and tails that telescopes can read. The orbit that brings it here is therefore more than a path. It is a trigger. It turns a silent archive into a temporary source of information. That this happens within the observational lifetime of a civilization able to interpret it is a coincidence impossible to quantify, but hard to ignore. The long journey itself is invisible, but its effects are written everywhere in the brief, bright passage that follows. The idea that 3I Atlas carries a normal comet inside a strange shell does not appear fully formed. It emerges as researchers try to reconcile scattered facts that at first do not seem to belong together. There is the early dominance of carbon dioxide in the coma, the strong and persistent anti-tail that points toward the Sun, the triangular arrangement of jets, and the later surge of water, once the object passes close to the star. Each of these observations can be interpreted on its own, but when they are placed side by side, a single framework becomes attractive. That framework is the radiation crust hypothesis, the proposal that the outer layer of the interstellar nucleus has been chemically and physically altered by prolonged exposure to galactic cosmic rays, creating a processed shell over a more ordinary water-rich core. To test this idea, scientists turn to laboratory experiments that simulate cosmic ray processing on ice mixtures. In controlled chambers, thin films of water ice combined with carbon-containing molecules are bombarded with high-energy particles meant to mimic the effect of cosmic rays. Over time, the original spectral signatures of water and simple organics change. New features appear that correspond to oxidized products, including carbon dioxide. The surface darkens and becomes less volatile. When the processed ice is warmed, it releases a different mix of gases than the fresh material underneath. These experiments cannot run for millions of years, but they provide a scaled proof that sustained radiation can transform the outer layers of icy solids into chemically distinct crusts. The results match the basic pattern observed in 3I Atlas, a surface that exhales more carbon dioxide than water when first heated, despite the likelihood of substantial water deeper inside. Theoretical models extend this reasoning. They calculate how far cosmic rays of different energies can penetrate into a small, icy body, and how quickly they convert the starting materials into new compounds. The penetration depth is not uniform. Higher energy particles can reach tens of centimeters or even meters, while lower energy ones deposit their energy closer to the surface. Over very long times, the cumulative effect is to process a layer whose thickness depends on both the energy spectrum of the incoming particles and the density of the material. For an object that has spent hundreds of millions or billions of years in interstellar space, these calculations suggest that a significant fraction of its outer shell would be altered. Beneath that layer, at depths beyond the reach of the bulk of the cosmic ray population, the original composition should remain largely intact. When such an object passes near a star for the first time, the heating sequence should follow the structure created by this history. The processed shell begins to sublimate at relatively low temperatures, releasing carbon dioxide and other radiation products. Later, as heat penetrates deeper, the untouched water-rich interior begins to respond. This is precisely the sequence that radio and infrared observations record in the case of 3I Atlas. The water surge near the closest approach to the Sun marks the moment when the heating wave crosses the boundary between the crust and the core. The radiation crust hypothesis therefore offers a coherent way to connect the chemical evolution of the coma with the long interstellar journey reconstructed from orbital dynamics. It also provides a natural explanation for some of the odd mechanical behavior. A crust that has been altered by cosmic rays is likely to be brittle and structurally complex. The breaking and reformation of chemical bonds combined with micrometeoroid impacts over vast spans of time can create a porous fractured network. When internal pressure from sublimating ices builds beneath this network, it will not necessarily break in a uniform way. Instead, gas will exploit existing weaknesses, opening vents along particular fracture lines. This can give rise to localized jets that remain stable over many rotations, as gas repeatedly chooses the same low-resistance paths to escape. In 3I Atlas, the triangular arrangement of jets and the stubborn antitail may both be manifestations of this preference. The sunward-facing jet could emerge from a region where the crust is relatively thin and weak, allowing deeper reservoirs of gas to punch through despite the opposing solar wind. The side jets might follow fractures that radiate from a larger cavity. The fact that the jets appear in a pattern rather than at random locations supports the view that the crust has been pre-structured by its long exposure to radiation and impacts. Yet the hypothesis is not a complete solution. When researchers run detailed simulations with realistic crust properties, some aspects of the observations are easy to reproduce while others remain elusive. For example, the timing and magnitude of the transition from carbon dioxide dominance to water dominance can be matched with a plausible range of crust thicknesses and thermal properties. The overall brightness evolution of the coma can also be brought into line with models that include a processed outer shell. However, the strength and persistence of the antitail through a wide range of viewing geometries are harder to justify solely through crust-controlled venting. Projection effects and dust sheet formation still play an important role, but the exact balance between geometry and physics is not yet fully resolved. In some models, the antitail fades more quickly than the data indicate. This suggests that either the jets are stronger or more finely collimated than the initial assumptions allow, or that the distribution of dust grain sizes in the coma is unusual. Larger grains are less affected by the solar wind and can maintain a sunward configuration longer, so a crust that preferentially releases such grains would help sustain the antitail. This in turn implies something specific about the grain size distribution in the processed layer, which future models must address. There are also small discrepancies in the ratios of different gas species. The simplest radiation chemistry pathways predict certain proportions of carbon dioxide, carbon monoxide, and other products. The measured composition of 3I Atlas's outer coma matches some of these ratios, but not all. In particular, some models would expect more complex organic residues than current spectra clearly show. It is possible that these residues are present but hard to detect at the available sensitivities masked by dust or blended with other lines. Alternatively, the starting composition of the comet before processing may have been different from the mixtures used in laboratory and theoretical work. Perhaps the original ice contained less of certain precursors, or the conditions in its birth disk favored different initial ratios. These uncertainties do not overturn the radiation crust hypothesis, but they remind researchers that it is an approximation built on incomplete knowledge of the starting materials and the full range of cosmic ray energies. The hypothesis also intersects with questions about mechanical integrity. A crust that is heavily processed and porous might be expected to fail catastrophically when stressed by internal pressure and thermal gradients breaking apart, rather than opening a few narrow vents. Some comets in the Sun system have indeed fragmented during close passages, leaving multiple nuclei and disrupted trails. 3I Atlas, however, remains intact throughout its encounter, at least to the limits of current resolution. This indicates that the crust and the underlying core retain enough cohesive strength to withstand the stresses of heating and outgassing. One way to reconcile this is to imagine a structure where the processed layer grades into the core gradually rather than ending in a sharp interface. The transition from heavily altered to relatively pristine material could occur over some depth, with mechanical properties changing smoothly. In such a configuration, cracks can propagate and widen without completely destabilizing the object, and strong jets can be sustained without wholesale breakup. Again, this is consistent with some, but not all, laboratory findings, and it pushes experimentalists to explore broader ranges of ice mixtures and temperature histories. Another intriguing consequence of the radiation crust hypothesis is that it may explain why 3I Atlas initially looked so unusual compared with previous interstellar visitors. The first known interstellar object detected passing through the solar system is a body that shows little or no coma, suggesting a different composition, or a thicker insulating layer that prevents substantial outgassing. The second is a more classical comet-like object whose behavior fits more closely with familiar patterns. 3. I Atlas sits between these examples, carrying a thick processed shell, but thin enough that the sun can eventually penetrate to active ice. If these three objects are all drawn from the same broad population, their differences may reflect variations in crust thickness, composition, and approach distance. The unusual features of 3I Atlas might then be an accentuated expression of a common interstellar process, rather than an outlier. Testing this idea will require more examples, but the radiation crust framework provides a lens through which to interpret them when they appear. For now, it stands as the most comprehensive attempt to connect the observable behavior of 3I Atlas to a simple physical story. A water-rich nucleus forms in a distant planetary system. It is ejected into interstellar space by gravitational interactions with massive planets. Over immense time, galactic cosmic rays convert its outer layers into a chemically distinct shell, dominated by carbon dioxide and other products. The object drifts until it encounters the sun, where heating first strips off the processed layer, then breaks through to the deeper ice, altering its coma chemistry and feeding unusual jets shaped by the crust's fracture network. This narrative leaves room for details to be revised, but it ties together widely separated phenomena into a single chain. Importantly, it frames the strangeness of 3I Atlas as the outcome of long-term natural processes, rather than as evidence of deliberate construction. It does not eliminate all anomalies, and it does not claim to answer every question. Instead, it offers a working picture whose remaining mismatches point the way toward further investigation. The radiation crust hypothesis does not end the mystery. It reshapes it into more precise questions about how icy bodies respond to billions of years of radiation, and how often similar shells might be found on other interstellar wanderers that have yet to be seen. When an object like 3I Atlas appears in the solar system and begins to behave in ways that stretch existing models, attention does not stay confined to its chemistry and dynamics. It also turns naturally toward the possibility of signals. Modern astronomy has built an infrastructure not only to study stars and comets, but also to listen in a structured way for evidence of technology beyond Earth. Institutions devoted to the search for extraterrestrial intelligence maintain instruments and analysis pipelines designed specifically to pick out artificial patterns from the noise of the cosmos. When an interstellar visitor with unusual traits appears, these systems respond. The reasoning is straightforward. If a distant technological civilization ever chose to send probes or instruments to other stars, those devices might not advertise themselves openly. They could drift dark and quiet for long periods. But if they communicated with a parent system or among themselves, they might emit narrow radio or microwave signals, structured pulses, or other electromagnetic signatures that differ from the broad natural emissions produced by simple physical processes. A small object on a hyperbolic orbit arriving from interstellar space and showing odd jets and tails becomes a natural target for such a search. Observatories that normally survey large regions of the sky narrow their focus and point their dishes and antennas toward the coordinates of 3I Atlas as it moves. In this phase of the campaign, the comet is no longer just a physical body. It is also a potential transmitter location. Arrays of radio telescopes sensitive to a wide range of frequencies record long tracks as the object passes through their fields of view. They do not look for a single specific type of signal, but for any deviation from the complex but statistically regular noise produced by natural astrophysical sources and the instrument environment itself. To separate sky from local interference, they shift beams slightly, compare on-target and off-target observations, and apply filters that remove known terrestrial sources. The analysis routines search for narrowband spikes, repeating patterns in transient bursts that remain spatially associated with the comet's position. Other instruments operate at optical and infrared wavelengths, sensitive to flashes or modulations that could indicate directed beams or high-power transmissions. Specialized spectrographs take high-resolution spectra of the coma and tail, searching not only for chemical lines, but also for any finely spaced structure that could hint at artificial modulation. In some campaigns, microwave detectors monitor the sky near the object, extending the range of frequencies under watch. The sensitivity of these systems is such that at the distances involved, they could detect continuous transmissions far weaker than those produced by common human devices if they were beamed toward Earth. The search continues over many days and weeks as 3I Atlas approaches its closest point to the Sun and then begins to recede. Observers time their sessions to cover different rotational phases of the nucleus in case any emission is tied to specific surface regions that rotate in and out of view. They also coordinate between sites in different parts of the world so that gaps in coverage from daylight or weather are minimized. In the data streams that return, there is no shortage of structure. The radio sky is full of bursts and lines from pulsars, masers, and flaring stars. Human technology adds its own layer of interference from satellites, aircraft, and ground-based communications. The challenge is to distinguish something that is both clearly artificial and clearly associated with 3I Atlas. Automated algorithms flag candidate signals that are then examined by human teams. Each promising feature is traced through time and compared across different pointing positions. If a spike appears only when the telescope is aimed at the comet and vanishes when it looks away, that is encouraging. If it follows the comet's motion across the sky, that is more encouraging still. But most candidates fail these tests. They persist when the telescope shifts, or they drift independently of the comet's path, revealing themselves as unrelated background sources or local interference. As the campaign progresses, the absence of a clear, persistent artificial signal becomes a result in itself. Sensitive upper limits are placed on what kinds of transmitters could be present. At the distances and coverage achieved, a device broadcasting continuously with even a small fraction of the power of common planetary radar systems or cellular networks would have been detected if it were beamed broadly or toward Earth. Short, infrequent bursts are harder to exclude, but repeated monitoring over multiple rotations of the nucleus reduces the space of possibilities. No regular pattern emerges that would indicate a deliberate beacon or data stream. The silence is not perfect. The instruments record many natural and human-made signals. But when correlations with the comet's position and motion are tested rigorously, none survive. In addition to direct signal searches, scientists also consider more subtle technosignatures features that could hint at technology without requiring active communication. These include unusually precise light curves that might suggest engineered surfaces, non-natural thermal emissions that indicate waste heat from machinery, or anomalous spectral lines that do not match any known chemical process. High-resolution photometric observations measure how the brightness of 3I Atlas changes as it rotates and as its viewing geometry shifts. The resulting light curves show variations consistent with an irregular outgassing body, not with a smooth rotating panel or a grid of reflectors. Infrared measurements detect heat from the sunlit coma and nucleus, but nothing that exceeds what would be expected from sunlight absorbed and re-emitted by a small icy body. The thermal spectrum lacks the distinct kind of excess that would betray active power sources buried beneath the surface. Spectroscopy, for its part, reveals emission from known molecules and ions in the coma. There are no sharp spectral lines at unlikely wavelengths that would suggest coherent artificial emissions. All of these negative results are in a strict sense provisional. They apply only to the sensitivity's frequencies and time windows that current instruments can cover. A highly advanced technology might use methods of communication or power that produce no detectable spillover in the bands being monitored. It might hide its presence, deliberately transmitting only briefly, narrowly, or in ways designed to blend into natural backgrounds. From that standpoint, the absence of signals cannot prove the absence of technology. It can only constrain certain classes of technological activity. However, the particular combination of constraints gathered during the 3i Atlas campaign is significant. It rules out the simple picture in which the object is, for example, a probe broadcasting robustly back to its origin on frequencies similar to those used by human technologies. It also eliminates scenarios in which large artificial structures cover the nucleus in ways that would create distinctive optical or thermal signatures. If technology is present, it must be subtle, hidden, or operating in regimes far outside those anticipated in current technosignature frameworks. For many in the scientific community, the lack of any compelling artificial signal strengthens the case for a purely natural explanation of the comet's behavior. The unusual jet's anti-tail and chemistry can be accounted for by the radiation crust hypothesis and related physical processes without invoking deliberate design. The silence from signal searches aligns with this natural picture. It is easier to explain the absence of transmission from a lump of processed ice than from an engineered object with access to power and communication tools. Yet the same observations also provide calibration for the broader search for extraterrestrial intelligence. They demonstrate how an interstellar object with genuinely anomalous properties appears under intense scrutiny when it is nevertheless natural. This helps define the baseline against which future candidates will be measured. The data from 3i Atlas show what kinds of non-gravitational accelerations, chemical oddities, and jet structures can arise from long-term natural processes. If a future interstellar vehicle were to display behaviors that clearly exceed these baselines, such as accelerations that cannot be reconciled with any plausible outgassing or spectral features that do not match any known chemistry, the case for artificiality would be stronger. In that sense, the null result from signal searches does not end the story. It refines the tools for reading it. The campaign around 3i Atlas also highlights the importance of rapid coordination. When the object was first recognized as interstellar and strange, it took time to mobilize the full array of instruments and observatories. By the time some facilities were fully engaged, the comet was already moving past its peak brightness. Future surveys and search strategies will likely incorporate lessons from this case, ensuring that when another unusual visitor is discovered, the response can be even swifter and more comprehensive. Ultimately, the absence of detected technosignatures from 3i Atlas must be placed alongside all the other pieces of evidence. The object moves along a hyperbolic orbit consistent with natural ejection from another star system. Its composition and outgassing patterns can be understood with some effort in terms of cosmic ray-processed crust and heated interior. Its jets and anti-tail, while uncommon, fall into the range of phenomena that can be produced by irregular structure and rare viewing geometry. The lack of artificial signals across a wide range of wavelengths and timescales strengthens this natural interpretation. But none of these observations can be extended beyond their own limits. They apply to one object observed briefly in a small corner of the galaxy. The silence around 3i Atlas is therefore both reassuring and incomplete. It suggests that this particular interstellar comet is not an obvious machine calling home, yet it leaves open the broader question of how many other wanderers, visible or unseen, might carry different stories. For the moment, the data say that 3i Atlas behaves and radiates like a complex but natural body. The absence of signals is itself a measured property, another entry in the growing catalog of how interstellar objects interact with stars and with the tools of a listening civilization. As the scientific picture of 3i Atlas becomes more detailed, another story grows alongside it, less about gas and dust, and more about human institutions and the way information moves through them. Public observatories publish their results, preprints circulate, and open databases fill with light curves and spectra. At the same time, certain parts of the response unfold behind closed doors. Government agencies with interests in space surveillance, national security, and intelligence gathering also track the interstellar visitor. Their instruments, many of which are not publicly described in detail, watch the sky for objects that might threaten satellites or reveal the capabilities of other nations. A fast-moving body on a trajectory from interstellar space draws their attention by default, even if only as a test of tracking hardware. In that context, the appearance of 3I Atlas inevitably touches systems that operate under classification rules. This intersection becomes visible in an indirect way when a group dedicated to archiving government documents invokes open records laws to ask what has been written about the object inside certain agencies. Requests of this kind are routine. Over the years, organizations and individuals have used formal channels to obtain files related to space events, military projects, and wider scientific topics. In many cases, the responses simply state that certain records exist and can be released sometimes with redactions. In other cases, agencies reply that no relevant records were found. The pattern is usually straightforward. The case of 3I Atlas produces something different. When one request is sent to an intelligence agency asking for communications and documents that mention the interstellar object, the reply does not fall neatly into the categories of confirmation or denial. Instead, the agency uses a careful formula. It states that it cannot confirm or deny whether responsive records exist, and that even acknowledging the presence or absence of such documents would itself be classified. This type of response has appeared in other contexts in the past. It functions as a legal and procedural device that allows an agency to avoid revealing sensitive information about its areas of interest, its methods, or its focus. In effect, it says that the question of whether the agency has paid attention to a particular topic is itself protected. Applied to 3I Atlas. This reply immediately draws attention. If the object is just an icy interstellar comet behaving in unusual but natural ways, why would the simple fact that internal discussions exist or do not exist be considered sensitive? The public imagination fills the vacuum with speculation. Some interpret the refusal to confirm or deny as an implicit suggestion that there is something extraordinary in the files. Others take it as routine caution, a reflex that has little to do with the nature of the comet, and more to do with the agency's broad policy of never mapping its interests too precisely for outside observers. In reality, both layers may be present. Intelligence organizations depend on being able to watch the sky with sensors whose capabilities and coverage are not fully disclosed. Those sensors may be tuned to detect faint objects, track high-velocity trajectories, and separate natural bodies from artificial satellites and debris. Any detailed internal discussion of a new object, like 3I Atlas, could contain information about how those systems work, what their limitations are, and what kinds of signals they prioritize. Even acknowledging that such discussions exist might reveal that the agency has enough interest and sensitivity in that region of parameter space to devote resources to it. From a security standpoint, that alone can be considered valuable information worth protecting in the same category as the raw data itself. If a foreign power can learn where and how an adversary watches the sky, it can better hide its own activities. In this light, a refusal to confirm or deny records about an interstellar comet may have little to do with the comet's intrinsic nature, and much to do with preserving uncertainty about surveillance. Yet the context in which this response arrives makes it hard to keep speculation contained. By the time the agency sends its carefully worded letter, public fascination with 3I Atlas is already high. The object has displayed a sunward anti-tail strange jets and a chemical profile unlike local comets. Discussions about its possible artificial nature have circulated widely, even as scientific studies have steadily moved the consensus toward a natural explanation. In that atmosphere, any hint of official secrecy feels loaded. The refusal to clarify whether internal documents even exist looks to some like confirmation that there is more to the story than the open literature reveals. This is the region where half answers thrive. On one side, Scientists publish their models openly describing how cosmic rays might have baked a crust, how water may have surged from the interior, and how the observed jets can arise from fractured terrain. On the other side, a government agency states only that the status of its own files is itself classified, offering no detail about their content or absence. Between these positions lies a gap that speculation rushes to fill. Some propose that the classified material might include detailed spectra from secret satellites revealing exotic elements or emissions that public instruments cannot see. Others imagine that precision tracking data could show non-gravitational motions that cannot be reconciled with outgassing alone. A more cautious view suggests that the documents, if they exist, probably contain mundane assessments of whether the comet poses any risk to assets in space or on the ground, and how its passage interacts with existing surveillance networks. Without access, it is impossible to know which of these possibilities is closest to reality. The structure of secrecy ensures that the ambiguity persists. The history of similar responses in other domains suggests that the safer interpretation is rarely the most dramatic one. Many past cases where agencies have taken the same stance have turned out to involve routine operational details rather than hidden discoveries. The reluctance to confirm or deny is often about preventing adversaries from mapping an intelligence organization's interests, not about concealing revelations. At the same time, the pattern demonstrates something important about how a technologically advanced civilization reacts when it encounters a new class of object. The reaction is layered. Scientific institutions focus on data and models, aiming to understand physical processes and place the object in context. Security institutions focus on implications for monitoring capabilities, risk assessment, and strategic knowledge. The same object therefore appears in two parallel stories, one written in journal papers and preprints the other in classified memoranda and restricted analyses. 3I Atlas happens to be a case where these two stories come close enough for their outlines to overlap in public view, even if their inner contents do not. For researchers working in the open, the presence of a parallel classified response can be both frustrating and motivating. On one hand, it suggests that additional data may exist that could refine or challenge current models but is not available. On the other, it underscores the importance of building as complete a picture as possible from unclassified observations, so that any future releases or declassifications can be immediately integrated and checked against independent results. For the broader public, the situation reinforces a more general lesson. Even when the best available scientific evidence points toward a natural explanation, institutional behaviors shaped by security and secrecy can make that explanation feel incomplete or unsatisfying. A small, icy body from another star system with jets and a strange coma is already a compelling object. Add a refusal from an intelligence agency to discuss whether it has records about that body, and the story acquires an additional layer of unresolved tension. This tension is not easily removed. The mechanisms that produce it are structural rather than personal. Analysts inside classified programs are bound by rules that speak in terms of sources, methods, and national advantage. Astronomers outside those programs operate with norms of transparency and peer review. The boundary between these domains is porous only in limited ways and often on long timescales. Documents that are shielded today may be released decades later, when the technologies and concerns they reference have aged. By then, the specific comet or event that triggered them may have faded from immediate memory, leaving historians to reconstruct connections. In the case of 3I Atlas, the open record already contains enough information to support a coherent physical narrative. The interstellar visitor follows a hyperbolic orbit, shows outgassing patterns that fit a radiation-processed crust over a water-rich core, and exhibits jets and tails that can be reproduced, if not perfectly, within refined models of dust dynamics and thermal fracture. Signal searches find no compelling evidence of artificial transmission. On these grounds, the simplest conclusion is that the object is natural. The parallel existence of half-answered questions in the classified sphere does not overturn this conclusion, but it does color the way it is received. The sense that something remains unseen lingers, even if what remains unseen is more likely to be technical documentation of sensors than extraordinary evidence about the comet itself. That lingering sense becomes part of the broader mystery that 3I Atlas represents. It is not just a question of what the object is, but also of how much any civilization can know about such visitors, given the limits of time, instrumentation, and institutional openness. Even when a consensus forms that the body is a normal comet inside a strange shell drifting in from another star, there remains an awareness that the full record of how it was observed, analyzed, and discussed will never be entirely public. Some pieces will stay locked away, others may be lost, and a few may surface later when they no longer carry operational significance. The object itself, meanwhile, continues outward, indifferent to these layers of secrecy. Its tail fades, its coma thins, and the vents that once carried water and carbon dioxide into space fall silent as it cools. In its wake, what remains in the solar system are archives, stacks of public data, private notes, and classified files, all reflecting different aspects of a single pass. The way these archives are divided and controlled becomes part of the enduring puzzle, a reminder that mysteries in astronomy are often shaped as much by human systems as by distant ice and rock. By the time 3I Atlas recedes beyond the reach of most telescopes, its influence inside the solar system is just beginning. The object itself is already dimming its coma, shrinking as heat leaks away and vents close. Dust that once traced elegant, confusing structures now drifts into a general haze that spreads along its outbound path. Yet in observatories, data centers, and research groups, the record of its passage continues to grow. Files are added, models refined, and comparative studies begin in earnest. 3. Atlas is no longer only a strange comet in the sky. It has become a reference point, a case study that future interstellar visitors will be measured against. One of the most important shifts it brings is a change in expectation. Before the first interstellar object was recognized, the possibility of such bodies entering the solar system was understood in theory, but not anchored in direct observation. Statistical estimates based on planet formation suggested that many star systems should eject countless small bodies into interstellar space. These wanderers would drift through the galaxy, and some fraction would inevitably pass near other stars. Yet until the first one was identified, this remained an abstract calculation. With the discovery of a second, and then with the arrival of 3I Atlas, as a third confirmed interstellar visitor within roughly a decade, the abstraction turns concrete. It becomes clear that the solar system is not isolated. It is embedded in a slow, ongoing exchange of material with the rest of the galaxy. 3I Atlas, with its radiation-baked shell and water-rich core, demonstrates that these guests can carry complex, layered histories. The timing of its appearance is significant. New survey facilities are coming online, designed to scan large portions of the sky quickly and repeatedly. Their wide fields and sensitive detectors are optimized to find transient events and moving objects, including small, faint bodies that older surveys might have missed. Among these facilities, next-generation ground-based observatories stand out. They are capable of imaging the entire accessible sky every few nights, building up a dynamic map of changing points. In such data, interstellar objects should reveal themselves as fast-moving sources on unusual trajectories, distinct from the slow looping motions of bound comets and asteroids. The detection of 3I Atlas occurs near the beginning of this new era, serving as a kind of preview of what these instruments will see more often in years to come. The expectation among many researchers is that as coverage improves and automated search algorithms become more sophisticated, the discovery rate of interstellar visitors will climb. Instead of one object every many years, there may be several. Over longer spans, dozens could be cataloged. Each will follow its own path, shaped by the dynamics of its birth system and its long sojourn in the interstellar medium. Each will carry a unique mix of volatiles and crustal chemistry. Taken together, they will outline a statistical portrait of how planet-forming disks behave across the galaxy. In that context, 3I Atlas is both a single data point and the first example of a particular subclass. Its combination of early carbon dioxide dominance, later water surge, and complex jets suggests that there exists a population of interstellar comets whose surfaces have been heavily processed by cosmic rays, but whose interiors remain broadly similar to familiar water ice bodies. Future discoveries will test how common this configuration is. Some objects may appear more extreme, with crusts so thick and insulating that no water ever escapes even near a star, making them appear dry and inert. Others may show only modest processing resembling classical comets from the solar system almost immediately. There may be bodies rich in other volatiles carrying signatures of more exotic birth environments. By comparing many such visitors, scientists hope to distinguish which traits of 3I Atlas are typical and which are unusual. Its anti-tail, for example, might turn out to be a rare consequence of a particular viewing geometry and crust structure, or it might be a recurring feature of interstellar comets whose dust distributions differ systematically from those of local bodies. The triangular pattern of jets might be an accident of fractured geometry unique to this nucleus, or a common manifestation of how radiation crusts crack and vent. Only a larger sample can decide. As these possibilities are considered, the role of advanced surveys becomes clearer. The window of maximum information for an interstellar object is often short. It enters the solar system faint and fast brightens as it approaches the sun, and then fades again as it departs. To extract detailed chemistry measure jets and search for subtle dynamical effects, observers must begin early and coordinate widely. The experience with 3I Atlas shows both the power and the limitations of current systems. Some instruments were in place and ready to react quickly, capturing key early spectra and images. Others needed time to schedule observations and adjust priorities. In future cases, the hope is that real-time alerts and automated classification tools will trigger deep follow-up more rapidly, ensuring that the most diagnostically useful phases are covered. Beyond the technical and logistical lessons, there is a deeper scientific shift. With every interstellar object that passes the solar system, becomes less of a closed laboratory and more of an intersection. Each visitor arrives from a specific set of circumstances elsewhere and leaves behind a trail of data that can be read as a sample from that environment. 3I Atlas suggests that some of these environments produce comets that are at their core broadly similar to those around the Sun, shaped by water ice and simple volatiles. Others may not. Over time, patterns will emerge. If many interstellar comets share comparable bulk compositions, that will hint at a kind of universality in how cold outer regions of planetary systems condense and evolve. If some are dramatically different, that will point toward diverse chemical landscapes across the galaxy. In either case, the interstellar visitors will act as messengers carrying pieces of their origin systems into the reach of instruments built around another star. The search for technosignatures also evolves in light of these encounters. 3I Atlas serves as an example of how a natural object with unusual behavior appears under careful scrutiny. Its non-gravitational accelerations can be tied to outgassing once the crust structure is understood. Its complex jets and anti-tail can be modeled with realistic dust and gas physics. Its spectra, while peculiar, can be traced back to plausible radiation chemistry. Against this backdrop, the absence of artificial signals and engineered signatures becomes more meaningful. Future searches can use 3I Atlas as a calibration point when evaluating new candidates. If a later interstellar object shows accelerations, light curves, or emissions that lie clearly outside the envelope defined by natural cases like this one, the case for something more exotic will be stronger. In this way, understanding a strange but natural interstellar comet becomes a prerequisite for judging claims about artificial visitors. The presence of facilities dedicated to broad sky monitoring also raises the possibility that some future interstellar object may be caught long before it reaches its point of closest approach, perhaps even years in advance. If that happens, there may be opportunities to do more than watch from afar. Concepts for fast response probes or piggyback missions have been discussed in general terms, small spacecraft that could be launched on short notice and guided to intercept a newly discovered interstellar visitor. The feasibility of such missions is constrained by propulsion limits, launch readiness, and cost, but the scientific payoff would be immense. A close pass by an interstellar comet would remove many of the uncertainties that now cloud interpretations of remote data. Crust thickness, fracture geometry, grain sizes, and surface composition could be observed directly. In that scenario, 3I Atlas would be remembered as a bridge case, the object that sharpened models and highlighted what a flyby would need to measure to resolve remaining questions. Even without such missions, the accumulation of observational records will change the way planetary science thinks about small bodies. The traditional division of comets into classes tied to the solar system's own reservoirs will expand to include multiple families of interstellar comets, each associated with different kinds of parent systems and interstellar histories. 3. I-Atlas, with its radiation crust and buried water, will likely define one of those families. Its parameters, such as typical crust depth, degree of processing, and characteristic gas ratios, will serve as benchmarks. Much as the first comets mapped the structure of the Sun's outer regions, these interstellar counterparts will map conditions in distant disks and the density and energy of the galaxy's radiation fields. Through all of this, one fact remains constant. Each interstellar object that passes through the solar system is transient. The time when its inner structure is exposed to direct study is short compared with the vast span of its journey. 3I Atlas has been shaped over tens or hundreds of millions of years by processes that operate on galactic scales, yet it reveals its nature only for a few months in the inner light of a single star. The same will be true for those that follow. The work of capturing, analyzing, and interpreting their signals will always be constrained by that brief window. In the end, 3I Atlas leaves the solar system much as it entered, silent and small against the backdrop of the galaxy. What has changed is the way the local civilization beneath its path understands such visitors. The idea that an interstellar comet must be radically alien in every respect no longer holds. The object shows that a body born around another star can be both familiar in its core and strange in its surface, transformed by long exposure to cosmic rays into something that initially misleads simple classifications. It also shows that even when an interstellar visitor displays odd geometry, unexpected chemistry, and subtle non-gravitational motions, these do not automatically point to technology. Natural processes stretched over immense timescales and operating under different initial conditions can produce outcomes that look exotic from a local perspective. At the same time, the passage of 3I Atlas does not close the door on more unusual possibilities. Rather, it sets a baseline. It defines one way an interstellar comet can be weird and still be natural. Future objects may fall within this pattern or step beyond it. Some may be quieter, some more dramatic. Among them, there may be bodies whose behavior resists even the expanded models built in response to this encounter. The instruments that watch the sky, the archives that store data, and the frameworks that interpret it will all be shaped by what has been learned here. As 3I Atlas fades into the dark, the questions it raises remain. How many more such objects cross the solar system unseen? How varied are the worlds that surround other stars? How often do natural processes produce signatures that resemble those of technology, and how can they be distinguished? Each new interstellar visitor will add a fragmentary answer. Together, over time, they may trace a clearer picture of the galaxy's hidden traffic. For now, one small layered comet from another system has passed through the inner regions of this one, leaving behind a tangled record of jets, spectra models, and debates. It is gone, but the mystery it represents has widened, extending from a single path through the solar system to the larger question of how many messages, natural and otherwise, drift silently between the stars.